Hello and welcome back to HK Academy. In the previous videos we learned what CPU load is and how to measure it. But one important question remains. What actually happens when the processor runs out of time? Will the converter continue operating normally? Will the control loop simply become slower? Or will the entire system become unstable? In this video we will intentionally overload the processor on a real digitally controlled buck converter and observe exactly what happens as the CPU load approaches 100%. Let's investigate what happens when the interrupt execution time becomes longer than the interrupt period. Before starting the converter, let's first look at the software implementation. In this example, I will artificially increase the CPU load by adding unnecessary calculations inside the control loop. The additional calculations are implemented using a simple for loop shown here. The variable Imax determines how many iterations are executed. The purpose of these calculations is not to modify the control algorithm, but simply to consume additional processor time. The actual voltage control loop algorithm is still implemented inside the control fast loop function. Now let's run the converter. First, I will start the debug session. Now we just click here, run. Once the software has been loaded onto the microcontroller, I will start the converter by setting the start converter variable to 1. As you can see, the converter is operating normally. The input voltage is 9 volts. The output voltage is regulated to approximately 2 volts, what can be observed as well here. And the switching frequency is 200 kilohertz. On the oscilloscope, we are monitoring three signals. The first channel is the GPIO signal used to measure the interrupt execution time. The second channel is one of the PWM gate signals. And the third channel is the converter output voltage. As you can see, at the beginning we have Imax set to 0. This corresponds to the normal software implementation and the converter operates correctly. Now let's gradually increase the computational load. First I will increase Imax to 2. As expected, the execution time increases, but converter still operates normally. Next I will increase Imax to 4. Again, the interrupt execution time becomes longer, as you can also observe here, but the controller is still able to complete the interrupt before the next interrupt occurs. Now let's increase Imax once more. At this point, the interrupt execution time exceeds the available interrupt period. Notice that the GPIO pulse disappears completely. This means the processor never reaches the instruction that sets the GPIO output. This indicates that the control interrupt is no longer executing correctly. Interestingly, the converter output voltage still appears to be properly regulated. At first glance, everything looks normal. Here is also the confirmation that we have 2 volts on the output voltage. But let's verify whether the controller is actually regulating the output voltage. I will now apply a load step by enabling an additional load. If the control algorithm were still running, the output voltage would quickly recover to its reference voltage. Instead, the output voltage here rises to approximately 2.4 volts and remains there. The controller is no longer updating the PWM duty cycle because the control interrupt can no longer complete successfully. This demonstrates why CPU load is so important in real-time digital control systems. A converter may initially appear to operate normally even though the controller has already stopped executing correctly. Only when the operating conditions change does the problem become immediately visible. In practice, engineers often start debugging by checking whether the control interrupt is actually executing. If the interrupt is no longer running, excessive CPU load is one possible cause that should be investigated. Of course, many other issues can also prevent an interrupt from executing correctly, such as incorrect interrupt configuration, peripheral settings, or software bugs. But as we have seen in this demonstration, CPU load is certainly one of the first things worth checking. CPU load doesn't usually fail gradually, it often fails suddenly when the processor can no longer meet its real-time deadlines. Let's briefly summarize what we have learned. As we have seen, a CPU load close to 100% leaves almost no computational margin for the processor. Once the interrupt execution time becomes longer than the interrupt period, the controller can no longer execute the control algorithm in a deterministic manner. As a result, the control performance may degrade, and in some cases, the converter can even become unstable. For this reason, it is always good engineering practice to leave sufficient computational margin for additional software tasks, communication, protection routines, and future software extensions. But this naturally raises another important question: how much CPU load is actually acceptable in a real digital power applications? Should we aim for 20%, 50%, or is 90% still perfectly acceptable? We will answer these questions in the next video by discussing practical CPU load recommendations and the engineering trade-offs behind them. Thank you for watching, and I will see you in the next video.